Hello, everybody. This is the first time we've done online notes in a little while, so just a little bit of reminders. Um, if you have, well, first off, hit pause so you can copy some things down, and then you can listen to me. Excuse me. Then you can listen to me explain some things. Um, the other important thing is to write down some questions as I'm talking about stuff. If you have a question about anything, just write that question down on the side of your notes and ask them when you get into class. Okay? So, a long time ago we skipped over chapter 6. We are going to now do that. Exponential functions, logarithmic functions is the gist of the chapter. Basically, just dealing with exponents. And so we start out with a standard topic, exponential growth and decay. I think you've seen this kind of stuff before, but it's all fairly basic. So, exponents, repetitive multiplication by the same number. You know that, and I think I misspelled repetitive there, but couldn't find the right version of it. That's all exponents are, it's just repetitive multiplication. All right, then you got this two kinds of things, exponential growth and exponential decay. Growth means its values are going up, decay means values are going down. Exponentially just means you're multiplying by the same amount every single time. And so we call that thing a rate, that amount that we're multiplying by. The rates that you use to multiply can be percentages, or things like doubling, where you're multiplying by 2, or it could be tripling every time frame, multiplying by 3. Just multiplying by 3 a bunch of times. So, if the rate that something is going up or down is a percentage, if it's a growth, you still have the original 100% of the material, whatever we're talking about, this population, bacteria, whatever. You still have 100%, but then you're adding on that extra percentage. That means you've got 105% if it was a growth rate of 5%. So you're dealing with 105%. So we're talking about exponents, which means you're multiplying. So take that percentage, turn it to a decimal. Our multiplier would be 1.05. That's what we would multiply by every single time frame. You know, if it's growing at 5% per year, every year you multiply by 1.05. If it was a decay, now we're talking about subtraction. We're taking away, getting a smaller value. So you got 100% less 5%. And so then again, that's 95%. Turn that to a decimal, the 0.95 becomes your multiplier. So, with all of these problems, we're talking about the basic problems. We are dealing with a same basic equation. All right, you have a final amount, called it A, and you have a starting amount. It's an initial amount, it doesn't matter what you're talking about, just how much are you starting with. We call that value the P. And then you multiply by your rate, that is R, and every time frame, whether it's per year, per month, every hour, how many of those time frames. So every time frame that goes by, you're multiplying by R again. There's your exponent. All right, so a couple of examples. Find the multiplier. So if it's a 9% growth, you've got 100% of your value, you're adding 9%. For a whopping 109%, but the multiplier is 1.09. Just turning that into a decimal. For a 2% decay, same idea. 100% minus 2% is 98%. The multiplier would be 0.98, just moving the decimal 2 spots. All right, this problem, again, just doing some standard problems. They're all the same basic idea of just how much am I starting with, how much am I growing or decaying, and how many times do I need to multiply by that amount. So, this basic example, it says predict the population of bacteria for each situation and time period. So 55 bacteria, that doubles every hour. So the question is, how much bacteria is there after 3 hours? So we're looking for A. We started with 55. The bacteria doubles. That means we're going to be multiplying by 2 a certain number of times. and this is after 3 hours. So it doubles every hour. So that means we're going to take 2 to the third power. All right, if you think about this, we start at 55. After 1 hour, double it. After another hour, double it. So we multiply by 2 again. After the third hour, double it. There's our answer. So 55 times 2 to the third power, we get 440. Bacteria, whatever it is. Same idea for after 5 days. How much is there? If we started with 55 and we are doubling it every hour after 5 days, okay? I did type all this stuff up at 2 a.m., so that might be a mistake, but let's just go with it. After 5 days, well, 24 hours per day, that is going to be 120 hours. This is going to be a huge number, but we'll go with it. 55 times 2 to the power of 120 takes, that's a lot of bacteria, 7.3107 times 10 to the 37th, which basically means move this decimal 37 places. It's a big number. All right, and this last example that we'll do here. So suppose that you buy a car for $15,000 and that its value decreases at a rate of 8% per year. That would be an average rate. If you buy a brand new car, as soon as you take it off the lot, you lose about 10 to 15% of the value, and then each year you just lose less of a percentage, but 8% per year is a good average. So, buy a car for $15,000, its value decreases at a rate of 8% per year. Predict the value of the car to the nearest cent after 10 years. All right, so the amount is how much we started at, 15,000. Now, what are we multiplying by? Okay, we start out with 100% of the value. Each year, we're losing 8%. So each year we have 92% of its value. That means our multiplier is 0.92. Every year we multiply by 0.92. So for 10 years. And we get out the calculator because I'm not good with my decimals raised to powers of 10. So 0.92 to the power of 10 multiplied by 15,000. And so that's 6,515. This is to the nearest cent, so 0.83. Not too bad. Seems a little unrealistic for a 10-year-old car, but my truck is 10 years old, and well, that'd be awesome to get that much money for it if I sold it. Okay, that is it for this lesson. I hope you have a good day in class. Good night.